Hello students, welcome to the class. So today we will see the section 4.6 of the chapter chemical bonding and molecular structure. So we have already dealt with the part where we have seen the overlapping of orbital. Today we will use that to make some simple molecules. So this is the disclaimer. Now, as we have discussed the overlap part, so the formation of some small molecules, or especially the molecules of your organic compound like your ethane, so that would be very easy for you once you are aware about the only left concept after the overlap, which is hybridization. So today we will talk about that. It's very important lecture for the chapter chemical bonding and molecular structure. So we will see that what are the types of hybridization which involves s, p and d orbitals. Then we will use this hybridization to draw some simple covalent molecules. If I talk about the NCERT sections that we are going to cover today, so in that process we will cover the hybridization, which is NCERT section 4.6, then types of hybridization. Next is examples like your sp3, sp2, sp and all. Then we will move on to those elements which have d orbitals. Okay, so this sp3, sp2 and sp, they are only including atomic orbitals from s and p subshell, but here in this case we are seeing it from the d orbitals as well. Lastly, there will be a bonus topic. So this is a part of hybridization, I would say, mainly, but without learning this say whisper theory and hybridization altogether, you cannot get that part. So I will disclose that in the end of the lecture. Now let us begin our discussion on hybridization. So according to Pauli, what is hybridization? It is the process of intermixing of orbitals. Okay, so in this, orbitals mix with each other and those orbitals are of comparable energies, means there is a very small amount of energy difference between the orbitals that will combine to give you the new set of orbitals. So it's very simple. You take atomic orbitals, combine them, and they will result in a new set of equivalent orbitals, which we call them as the hybrid orbitals. So two parts are here. First, what is hybridization? So hybridization is the mixing of atomic orbitals and atomic orbital mix to form the hybrid orbitals. So if I talk about the important conditions required for this hybridization, then the first would be the orbitals which are present in the valence shell are the one which are used in the hybridization. So this is very important. You can only include the outermost shell or the valence shell for the making of hybridized orbital or hybrid orbitals. Now, next important point, if you are combining this orbitals of the valence shell, then their energies should be also comparable. Okay, so you can't take two different orbitals which are in a very different energy state. Suppose you can't take a 2s and try to combine it with the 4f. So that is not good. Now you don't know the exact, so at this point we don't know the exact difference between the orbitals, and I am hopeful that you will not need to do so also. Okay, so you don't need to see that whether these two will combine or not. You will never stand in that dilemma, but you should remember this point. Always take those orbitals for hybridizing which are almost equal energy or of comparable energy. Then the next important point is, so there is always a confusion in this point. Most of the students make a mistake of promoting the electron always while doing the hybridization. So this is never an essential condition to do the hybridization. If you are trying to hybridize two orbitals, right, then of course in those orbitals there will be electrons. So it can be one way or the other, like there may be promotion of electron or there may not be promotion of electron, both cases are possible. We will try to understand it later on, what is promotion and all. So basically it would be like unpairing the electrons, right? So that is called as promotion of electrons. Then it is also possible that both half-filled and full-filled orbitals can participate in hybridization. So both are capable of doing the participation in hybridization. So these are the 4 important conditions, right, to do the hybridization. Now we will move on to the properties of hybrid orbitals, that what are the characteristics these hybrid orbitals show, and it's very important to understand them. So let's see our next part, which is properties of hybrid orbitals. So hybrid orbitals are formed and they are used only for the sigma bond formation. So you should remember this, that hybrid orbitals are only used for sigma bond formation. Now if I ask you, how is the sigma bond formed? So 2 possible ways are there for a bond formation, sigma and pi. Sigma is formed by the side-on-side head-on-head overlap, and the pi is formed by the side-on-side or lateral overlap. So I am leaving this up to you, that how this will be formed by the side-on-side overlap or lateral overlap. Now moving on to the next one. Hybrid orbitals always form stronger bonds than atomic orbitals. So atomic orbitals will also form bonds, it's true, but those bonds will be less stronger than the hybrid orbitals. And the type of bond your pure atomic orbital be formed will always be pi bond. So you can take this as a thumb rule. If your molecule is containing 2 types of bond, sigma and pi, then sigma will be formed by the hybrid orbital and pi will be formed by the pure atomic orbitals. Got it? Now next, the most important point, that they always have equal energy and same shape. They all will be of the same shape and their energies will be equal, no matter which atomic orbitals are used up in making those hybrid orbital. Okay. So in a molecule, always remember, if you are considering it for the one atom and the atomic orbital of that atom is combining to form a set of hybrid orbital, then their energies will be, the energies of those orbitals will be always same. Now, do not confuse it with other statement like the hybrid orbital of 2 atoms can be same in energy and shape. So that would be a wrong part to consider. Always remember, in a given atom, okay, in one atom, the hybrid orbitals which are formed, they will be always of same energy. Is it clear? Now next, the number of hybrid orbital is equals to the number of atomic orbitals that are used to make those hybrid orbitals. So if 2 atomic orbitals are combining, 2 hybrid orbitals will be formed. Then last and the most important point, hybrid orbitals are directional in nature, means they orient themselves in a proper direction. Now why are they doing it so? They are doing it so to minimize the electron pair repulsion. So this minimization of electron pair repulsion, it leads to a stable molecular arrangement, and this arrangement is responsible for the type of hybridization which indicates your geometry of the molecule. So 3 things are there. First of all, your hybrid orbitals are directional. Second thing, if they are directional, the reason of this directionality is the repulsion. So to avoid repulsion, they are directionating themselves in a proper order, and this leads to a stable molecular arrangement which we call as the geometry of the molecule. I hope all of these points are clear to you, and I would suggest you to learn all of these points by heart. Now this will be the basis of your further discussion. Now again I am repeating what are the important points. First is hybrid orbitals are used in sigma formation. Second point, atomic orbitals are used in pi bond formation. Third is sigma bond will be stronger than pi bond. So this will be obvious. So therefore you can say that the bonds formed by the hybrid orbitals will be stronger than the bonds formed by the atomic orbital. Then next, all the hybrid orbital of a given atom will be equal in shape and energies. Then next, they will be directional in nature, and this is done to minimize the electronic repulsion. And last point, the atomic orbitals count will be equal to the number of hybrid orbitals that are formed. So if you are taking two s orbital and combining them, then the new hybrid orbital will also have two set of orbitals. I guess this part is clear to you. Now, if this part is clear to you, let us move on to different kind of hybridization. So what we have dealt till now, so we said that in hybridization, what we do the mixing of atomic orbitals. We know it very well that the atomic orbitals are used in the formation of bond. Now, why we are mixing it? The reason is that it is done to minimize the energy. You can see it here. They are mixing in order to get the hybrid orbital which are lower in energy, right? So that is the reason they are mixing with each other. And remember, after the mixing, the hybrid orbitals will be formed, and this will be their characteristics. Now, let us try to understand the first kind of hybridization, which is sp hybridization. Okay, now you are aware about, many of you would be aware about what is sp hybridization. But I will try to give you some points which are very, very important, right? And very, very specific, I would say. Now it is obvious, if sp hybridization is occurring, means one s and one p orbital, they are combining to form the new set of hybrid orbital. Now in this case, I am taking the molecule as barium chloride, which is BeCl2. So the second point is that now the beryllium will undergo hybridization here. And what will happen as a result of that? There will be formation of two equivalent sp hybrid orbital, which will be at an angle of 180 degree. Because two orbitals were involved in hybridization, so two will be formed. And which will be these two orbitals? This will be present in the valence shell, which is 2s and 2p. We know it. If you consider beryllium, then the valence shell, subshell for the beryllium is 2s and 2p. So they will be the one which will be combining. And not the subshell. Their orbitals will combine specifically. Okay. So this is the hybridization that takes place. Now you can see here that 1s and 1p, they are combining with each other, and this is the hybrid orbital that is formed. Now, if you ask where are the two orbitals, you said that two atomic orbitals will combine and simultaneously two hybrid orbitals will be formed. Okay. If you see here, you can easily interpret them. Okay, so these are the two orbitals. Okay, there is one positive here, and the corresponding negative is present on the right side. Similarly, on the right side there is a positive and its corresponding small orbital is present on the opposite side. So these are the two orbitals of beryllium which are formed, hybrid orbitals of beryllium which is formed, and they are at an angle of 180 degrees. Right? This shape will be called as linear, and it is very obvious from here. Now, what we can say, that the orbitals which are combining to form this sp will be s and pz. Now the question arises, why we are taking pz? Why can't we take py, px? So the answer would be, in the normal convention, sign convention, we take the z axis, right? So this is the most used up convention. So if your combination is occurring to the z axis, therefore we will always take the z axis, or I would say the pz. So why are we taking it pz specifically? Because in the case of pz only, the hybridization is possible. So similarly, like your, you can say the way your overlap happens, the requirement of same sign, the same requirement is here also, but the result is not same. Here it is not the case of overlap, so do not confuse it with the overlap. In this case, your two atomic orbitals are completely combining and creating new orbitals. They are not overlapping here. Okay, so that is a different thing. So do not confuse it with that thing. Right. Now, we know that for the sp hybridization, S and Pz are combining. And why it is happening? Because hybrid orbitals are lying along the z-axis. Now, next, what we know? That your 50% will be your S character and 50% will be your P character. Now, how did I calculate this? It's very simple. You know that two orbitals, atomic orbitals, are involved in your making of the hybrid orbital. So divide that 2 by divide that 2 by 100. Okay, so 100 by 2 will give you the 50% S and 50% P. It's very, very simple. So what you are doing is you are giving your character percentage of your hybrid orbital equally among your S and P, right? And you will do this same thing next onwards. Now the question arises, what is the use of this hybrid orbital? We have talked about it earlier that your hybrid orbital are used in the making of sigma bond, and we have those hybrid orbital. So let us now move on to the formation of this bond. So now what will happen? The sp hybrid orbital that you got, that will do a head-on-head overlap with the p orbital of each chlorine atom. So we were interested in the BeCl2. Therefore, this will result in sigma bond formation with the chlorine atom. So this is your diagram to represent it. So we have our beryllium hybrid orbital, and on both sides the sign is positive. The negative part is inside this. Okay. Now you do not need to every time represent the negative sign of the hybrid orbital. You should be just interested in the positive part, and you will see in most of the books also that this small lobe is being not represented. Next, what will happen? The pure atomic orbital. Okay, remember here the pure atomic orbital of your chlorine, which is Pz, it is combining with the hybridized orbital of beryllium, which is Sp, to form the sigma bond. And since it is a head-on-head overlap, therefore it will form a sigma bond. Similarly, your second chlorine will also do the same thing. It will use its valence shell atomic orbital to do a head-on-head overlap with the hybrid orbital of beryllium. I hope this point is clear to you, that how this beryllium chloride is formed. Step by step I have told you everything. Now the next information you should know is that this geometry is completely linear. Okay, it is aligning along the z-axis completely. There is no lobes that are not orienting along this single axis. So it is a linear geometry. Now this type of geometry is also called as the diagonal hybridization. So this is also very important term to remember, that this kind of hybridization is also called as diagonal hybridization. Now if I talk about BeCl2, and if you try to draw the Lewis structure, you will notice it very clearly that it has two sigma bonds, right, and no pi bonds. So therefore our Lewis structure is also being validated here easily with the help of this new BeCl2 molecule. So I guess your sp hybridization is quite clear to you. Now you can think of more examples that can do the sp hybridization. And the next question is for you, that if it is linear in shape, then what would be the steric number? Okay, so what would be the steric number for the given molecule, which is beryllium chloride? I am leaving this question on to you. So let us talk about the electronic rearrangement of the BeCl2. So what is happening inside the molecule on the electronic level? So we have seen what is happening to the atomic orbitals, right? Now what is happening on the electronic configuration, we should understand it. Yes, the correct answer will be 2. 2 will be the steric number of the linear geometry. We know that beryllium has a ground state of 2s2 and both of the electrons are paired up, right? But as soon as your chlorine atoms approach this beryllium to make bond, your beryllium will go on to the excited state. Now this is called as the promotion of electron. You can see it here that your initial electronic configuration of 2s2 has now been promoted. Your electron has been promoted from 2s2 to the 2p orbital. And now you are getting the configuration as 2s1 and 2p1. Is it clear? Right? So you can see there is promotion of one electron. So let us try to understand that same thing with the help of this diagram. So this is your ground state and this is your excited state. Now you can see that your 2s orbital here was initially doubly occupied. So 2 paired up electron. But after the hybridization, after the promotion of electron, your electron will go from here onto the next higher energy. Okay, and its spin will be also changed. Initially it was spin down, but after promotion it is again spin up. Now what is the next step in this? The next step is the hybridization. Which two orbitals will hybridize? S and Pz. Okay. So what we can say? That after the hybridization, 2 sp hybridized orbital are formed. And what are we left with? We are left with the 2 pure p orbitals. So again I am repeating it. Initially we have 2 electrons. This is the ground state. You can try to write the electronic configuration. You will get the same thing. After the excitation of one electron, you will have 2 unpaired electrons, one in s and the second in p. And these 2 orbitals will just hybridize to form the sp hybrid orbital, and rest of this will be the pure p orbital, which is being represented here. What will happen in the next part? These 2 unpaired electrons that are being formed as a result of this hybridization and unpairing, they will be paired up with the electrons of chlorine. We know that your chlorine can donate 1 electron, okay, or it needs 1 electron. So whenever you can say the overlapping of orbital were taking place, in that process, this pairing of electron is taking place simultaneously. So atomic orbital is what? It is nothing but your electron. It is your density of electron. So that diagram which I have shown you earlier, it was a pictorial representation. And that same thing is represented here also. But in this case, we have used the notation thing, which is quite simple to understand as compared to that thing. But this thing and that hybrid part both are completely same. They are not two different things, right? So do not confuse it with this. So after this, your 2 sigma bonds are formed because 2 electrons are paired up with the 2 electrons of beryllium. Now this is not the necessary case. I have told you in the start, remember that the promotion of this electron is not necessary. Okay, we will see an example where the promotion is not seen. Now moving on to the next type of hybridization, which is sp2 hybridization. Now what happens in sp2 hybridization? To understand that, we will take the case of BCl3, which is boron trichloride. Now, if boron is the central atom, it will undergo hybridization. And what are the orbitals that will be used in that hybridization? It will be a 1s orbital. Okay, so not the principal quantum number 1, means the counting one. Okay, so there will be an s orbital and 2 p orbitals. They will combine to form the new set of hybrid orbital. Now this hybrid orbital will be equivalent in energy, and the angle between these hybrid orbital will be 120 degree. Since 3 orbitals, 1s and 2p, are used to make the hybrid orbital, therefore 3 hybrid orbitals will be formed. And what are those two orbitals? Those two orbitals are present in the valence shell of the boron, which is 2s and 2p. I guess this is clear to you. Now, let us try to understand the same with the help of this diagram. Now, this diagram is given here. It may be quite confusing to you that you can't spot your px, py, pz and s orbital. So, it's very simple, right? You take the x-axis and you can see that two circles are drawn along this x-axis, right? One is containing a negative sign and the second one is containing a positive sign. So these two circles are representing your px orbital. Okay, this is your atomic orbital of px. Similarly, you can see two circles along the z-axis. Okay, the smaller one, not the black one, the blue one. Now this pz, this is the pictorial representation of pz. And the third orbital, which is s orbital, that is being represented with a larger circle, the black circle. This is representing your s orbital. Now what will happen? Your px, your py and your s will combine to give these three sets of hybrid orbital. You can notice them. There is a positive here and the opposite side there is a small negative. Similarly, here is a positive, small negative, positive and small negative. So these three orbitals, hybrid orbitals, are making an angle of 120 degrees. And this hybridization is called as sp2 hybridization. Okay, I hope this is clear to you. Now all of this is happening in boron. Again, I am repeating it. Here also, your hybrid orbital will lie along the z-axis. And next thing is that your sp2 hybrid orbital on boron has 33.3% S character and 66.7% P character. Now, how is this numerical value coming? You know that 3 atomic orbitals are involved. That means your hybrid orbital will have the characteristics of these 3. But these 3 will be distributed equally. That means 100 by 3. So for each s orbital and each p orbital, we will get 33.33%. As there will be only one s orbital, therefore the s character will be 33.3. Whereas there are 2 p orbitals involved in it, py and pz. So each one will get 33.3 and 33.3. We can add them and get 66.666 or 66.7 approximately. So it's very simple to calculate. It is simply distribution of your percentage along all the orbitals that are participating in the hybridization and nothing else. So we got our hybrid orbital, right? Now what are we interested in? We are interested in now making the bonds. How we'll do it? Again, your sp2 hybrid orbital will do a head-on-head overlap with the 3 chlorine atoms. Okay, and again your p orbitals, atomic p orbitals, will do this thing. Upon this head-on-head overlap, there will be formation of 3 sigma bonds with the pz orbital of chlorine atom. So this is your diagram. You can see that there are 3 chlorine atoms, 3 chlorine atomic orbitals which are making the sigma bond. Okay. Now, since it is sp2 hybridized, and if you take the steric number of this BCl3, it will be trigonal planar geometry. And this is quite clear with the shape of the molecule also. Now, let us look at how do we represent it through the electronic rearrangement. Again, the boron has a ground state of 2s to 2p1. This thing will be promoted, their electrons will be promoted, and you will get a 2s1 2p2. So you can see it in the diagram. There is initially 2s2 2p1. Now, as the electrons are excited, 1s will get your 1 electron, and the py and pz will get the rest of the 2 electrons. In the next part, what will happen? The two orbitals of p and the one orbital of s will combine to form the sp2 hybrid orbital, which will be singly occupied. Then one p orbital, pure p orbital, will be left here. Now for the formation of BCl3, what will happen? In the next step, each of the chlorine atom will do a pair up with the single electron of the boron to form 3 sigma bonds. Okay? I hope this is clear to you. Now, moving on to the next type of hybridization. Now I will try to move quickly here. So you already got the idea of sp and sp2. No, there is not such energy. Same energy is not required. So first of all, you should question this, that where is this energy coming from? What is the motive of this energy? All of this is happening because your central atom is being approached by different surrounding atoms. Like in the first case, your boron was attempted. Second case, your boron was approached by chlorine. In the first case, your beryllium was approached by again chlorine. So it depends on the approaching atom and the atom being approached, that how the energy will be supplied and which hybridization will take place. So all of those things are totally based upon the interaction of the two atoms that are occurring, right? So there is no fixed amount of energy that is used. If I talk about the sp3, one s orbital is there and it is combining with the 3 p orbitals of the central carbon atom. So here we are taking the methane molecule CH4. As a result, 4 hybrid orbitals will be formed, which will be at an angle of 109.5 degrees. And again, I have told it earlier also that in hybridization, you always use the valence electron. So the valence orbitals of the 2s and the 2p are used in this making of hybrid orbital. So this is your hybrid orbital. You can again just try to look here. So this is quite confusing. There is a y-axis, x-axis and a z-axis. Along all of this, there is a p orbital. And a whole circle is there on the top to represent the s orbital. They are combining together s, px, py, pz to form the sp3 hybrid orbital, which are at an angle of 109.5 degrees. So what are the orbitals which are involved in sp3? S, px, py and pz. And in this case also, your hybrid orbitals will lie along the z-axis. Now the question is that each sp3 orbital on carbon has 25% s character. Then what will be the character of p? So it's very simple. You are having 4 orbitals. There is 1 s and 3 p. Total of 4 atomic orbitals are there. The total percentage is 100. Divide 100 by 4. Therefore, your each s and each p will get 25% for the upcoming hybrid orbital. Therefore, what you will get? 3 p orbitals are there. So 25 for each p will make it 75 for the p character and remaining 25 it for the s character. Next will be the formation of bonds. Same thing will happen. Your sp3 hybrid orbital, it will do a head-on-head overlap with the s orbital with the hydrogen. Now here, you are using the s orbital of hydrogen and not the p orbital, and it is very obvious. Hydrogen's valence orbital is s only. The case of p orbital was true for chlorine. So this will be the formation. You have a sp3 hybrid orbital of carbon, and with each lobe, your hydrogen's pure atomic orbital of 1s is doing a head-on-head overlap to form 1,1 sigma bond respectively. Okay? And this results in your tetrahedral geometry. So this is why this is called as tetrahedral, because 4 atoms are there that are used to make it. And 4 means tetra, and the formation of this structure is called as tetrahedral geometry. Now let us move on to the electronic rearrangement that is taking place in case of methane. If I talk about the ground state of carbon, it is 2s2 2p2. There are 2 paired electrons in S and 2 unpaired electrons in 2p. When the electron is being excited, you will get a different kind of hybridization. Not hybridization, the pairing up. What will happen? There will be one electron promotion, and this will result in 4 electrons, okay, in the P. Not in the P, sorry, 3 electrons in the P. So 1 in the S and 3 in the P. So total there are 4 unpaired electrons. Got it? Again, since it is sp3 hybridization, each of these singly containing atomic orbitals will combine to form the sp3 hybrid orbital. Now, in this case, there are no pure p orbital because all of the p orbitals are used up in making the hybrid orbital. Now, what will happen when the hydrogen will come and donate its electron? Each of the electron will be paired up with the hydrogen single electron, and that will result in 4 sigma bond. I hope this is clear to you. It's very simple to understand, right? Now the question is that how we are deciding that how many electrons will be unpaired? Will it be unpaired or not? Though your answer lies in your steric number. Once you got your steric number, you are already knowing that it is a sp3 hybridization. If you are getting the, say, your steric number as 2, surely your geometry is linear, and if you are getting it as 3, your geometry is trigonal planar. Okay, so from that part you can get the hybridization without doing all this stuff. Now let us compare a very interesting case here, which is the case of ammonia and water molecule. If you calculate the steric number of both of this, you will find that they both have the steric number of 4. But their original geometry and shape are completely different. The shape is so completely different that your NH3 is trigonal pyramidal, whereas your water molecule is having a bend shape. But the geometry is same, but the part is that your bond parameters and angles are not same because of the involvement of lone pairs. So we will see that in case of ammonia molecule, it is distorted, right? Because of this lone pair, it is distorted, and due to extra repulsion, the angle is changing from 109.5 degrees to 107 degrees. Okay? Whereas due to 2 lone pairs, in the case of H2O, your angle is going from 109.5 to 104.5 degrees. So even smaller angle is seen. But again, both of these will have the sp3 hybridization and tetrahedral geometry, but a different shape, V shape or the bend shape in case of water, whereas pyramidal shape, triangular pyramidal shape in case of ammonia molecule. Remember, in the case of shape, we only take the molecules and not the lone pair. Now let us talk about those elements which have d orbitals in them. There are 4 such kinds that are being mentioned here. Today we will discuss only square pyramidal and your octahedral, because these 2 are important. Now the question is that in case of 6 steric number, 2 are possible, square pyramidal and octahedral, but you will often see in your notebooks that it is octahedral. Okay. Similarly, for your steric number of 4, you often see the tetrahedral. Square planar is not that much prominent. In the case of 5, the shape will be trigonal bipyramidal. Now remember this hybridization. The first one is dsp2. Again, 4 orbitals are involved. Trigonal pyramidal, 5 orbitals are involved. So the hybridization is also same, and the steric number also 5. Square pyramidal, 5 atomic orbitals are involved. Sorry, 6 atomic orbitals are involved. So 6 is the steric number. And lastly, octahedral also has 6 hybrid orbital, which is sp3d2 or d2sp3, which results in steric number of 6. Now we will talk about them in detail. So for the case of sp3d, I am taking the formation of PCl5. Okay. Directly, I am using this electronic representation. It is very difficult to show the hybrid orbital formation with the combination of atomic orbital. Okay, so I'm using this notation. So this is the reason we use this, not the actual one. It makes our life simple. So we have the ground state, phosphorus. Okay, this is being excited and we get an electron unpaired and that goes to the d orbital. Easy. Next, what will happen? 5 chlorines are there. They will each will donate its electron onto the chlorine atomic orbital and we will get the sp3d hybridization. I hope this is clear to you. So we can say that in the bond formation of PCl5, two things are happening. First, your phosphorus is undergoing hybridization to form the sp3d, and second, in this process, all of these electrons are being unpaired up. Okay, so the 3s electrons are getting unpaired, and lastly, the 5 chlorine atoms are overlapping with the phosphorus to pair up the unpaired electron, and then we are getting 5 sigma bonds here. Now, what will be the shape? Of course, the bond angle in trigonal bipyramidal geometry will be not equivalent for all of the bond angles. So this is very, very important here. If you look at the trigonal bipyramidal shape, it looks like this. Okay, so there are 3 chlorine atoms in a triangular shape and 2 chlorine atoms perpendicular to that. In this overall structure, 2 bond angles are possible. In the previous cases, you must have seen only one type of bond angle, but here 2 bond angles are possible. One is 120 degree and the second one is 90 degree. So for those which are lying on the plane, see on the red plane, it is making 120 degree with each of the chlorine. Whereas the one which is lying axially, it is making a 90 degree angle. Okay, is it clear? Now, an important point here. There are 2 types of bond also. The first one is called as equatorial. Why it is called as equatorial? Because it is along the equator. So 3 PCl bonds are there and they all are in the same plane, which is this red plane. And they all bonds are called as equatorial bonds. And each of these is making an angle of 120 degree. Now what about the axial bonds? So this axial bonds, you can see it here that it is perpendicular to this equatorial plane. Therefore, it is making an angle of 90 degree and 2 such chlorine atoms are possible. Okay. So we can say that there are some bonds which are making a 90 degree and they are making it with the equatorial plane. So I hope this structure is clear and the bond angle is clear till now. For the case of trigonal bipyramidal, you must try to draw this shape by your own. Now, let us discuss a very important point. It is often asked in your exam. The point is that there is always an elongation of axial bonds. Let us try to understand it. Why is this happening? So basically, it is seen that in the case of bond length and reactivity, the axial bond, they experience more repulsion. Why are they experiencing more repulsion? Because they are having 3 bond pair repulsion. If you see the equatorial, they are experiencing 2 bond pair repulsion, one from the top chlorine and one from the bottom chlorine. But for the case of axial, there are 3 90 degree chlorine bond pair to this axial chlorine atom. As a result of it, it is experiencing more repulsion and therefore this axial bond elongates, its distance is increased and this thing is increasing to reduce the repulsion. So we have seen the same case for the case of lone pair. So this was the reason your lone pair always lie on the equatorial position, because there are 3 bond pair repulsion for the axial bonds. To overcome that thing, your phosphorus and chlorine distance increases on the axial positions, and due to this lengthening, these bonds are also less stronger, or I would say they are weaker than the equatorial bond. So 2 things are there. Axial bonds are longer than the equatorial bond and axial bonds are weaker than the equatorial bond. And this differentiation in their bond length makes your PCl5 very reactive. Okay, is it clear? So it's very, very important to understand this. So you can see here that due to the repulsion, the axial bonds will be longer than the equatorial bond, and as a result, your PCl5 is reactive and the axial bonds are weaker than the equatorial ones. Now let us move on to the next type of hybridization, which is sp3d2 hybridization that occurs in the case of SF6. If you look here, you would see that there is a sulfur atom, right? So again, the same thing. The sulfur atom is in the ground state. It is going to the excited state. And lastly, each of this is getting paired up by the 6 fluorine atoms. Okay, so there is nothing much to explain in this. We have already gone through this multiple times. And how do you know that how many electrons will get unpaired up? It's very simple. You know the final geometry because of the steric number. Since the steric number of SF6 will come out to be how much? It will be 6. So it will be, of course, octahedral. Now, this is the electronic configuration of SF6. First, it is 3s2, 3p4 in the ground state. Then it is going to the excited state where your s orbital, p orbital and d orbital are getting a singly occupied state. After that, your fluorine atom is overlapping with the sulfur atom, and in this process, each of that electrons are getting paired up to form 6 equivalent sigma bonds. Now the question is that what will be the shape and the hybridization? The hybridization will be what? It will be sp3d2, and in that shape, your 6 corners of a regular octahedron will be occupied by the fluorine atom. So this is your SF6. In the central, we have the sulfur, and each corner of the octahedron, we have a fluorine atom. Now in this case, there is no elongation of bond or no shortening of bond. Each of the bond lengths are identical to each other. Clear? Now, let us try to use all of this knowledge and do it for a complex molecule, which is C2H4. We will go step by step. First of all, we will draw the Lewis structure of ethene. So this C2H4 is nothing but your ethene. Then, after that, we will do the structure determination. So we have seen it earlier that for the steric number of 3, your shape will be trigonal planar. So we can say that both of this carbon will be trigonal planar in shape, and both will be sp2 hybridized, because trigonal planar means sp2 hybridization and it is directly coming from the steric number. Then what will happen on the next part? We know that our both of the carbon are sp2 hybridized. Okay. Now this sp2 hybridized carbon will firstly do an head-on-head overlap with each other. So in the formation of sigma bond, what will happen? The one carbon which is sp2 hybridized will overlap with the second carbon to form a sigma bond. Then the second type of sigma bond will be formed by the head-on-head overlap of the atomic orbital of hydrogen, or specifically the s atomic orbital of the hydrogen. So we can say in this case of ethene, 2 types of sigma bond are formed. First, due to the head-on-head overlap of 2 sp2 hybridized orbital of carbon, and second is head-on-head overlap of 1s orbital of hydrogen with the sp2 hybridized orbital of carbon. Okay. Now, you have seen it in the previous case that your carbon has how many sigma bonds? 5 sigma bonds and 1 pi bond. But your pi bond is not formed by the hybrid orbital. It is always formed by the atomic orbital, and I have told you in the start. Now let us focus on that, how that pi bond will be formed. I guess this part is clear to you. Now let us try to understand the formation of pi bond. We know that our pure p orbital is being left out. If you remember the case of sp2 hybridized, you must see that only 2 p orbitals are involved and one pure p atomic orbital is already left on the carbon. So what will happen now? These 2 p orbitals will do a side-on-side overlap. And as these two are present on the same plane, now remember students, if 2 p orbitals are combining, if you see here, then they must be on the same plane. You can see it very clearly that these two are on the same plane and that plane is perpendicular to the plane of the molecule. Got it? Now they will do a side-on-side overlap and as a result your saucer type will be formed. We have seen this kind of overlap. Right? So there will be a side-on overlap which will result in a pi bond. Now do not take it as 2 pi bond because only 2 atomic orbitals are there which are making bond. So therefore these 2 atomic orbitals will make 1 pi bond. So this two lines are not representing 2 bonds individually. They are just representing that how they are combining. The upper part is combining with the upper part. The lower part is combining with the lower part to form 2 saucer lobes. And these lobes are where your electrons will be there. Okay. So I hope you got this. It's very, very important to understand this part because most of the students are finding it very difficult to understand this formation. Now I would suggest you to similarly and go and try it for the ethyne molecule, which is C2H2. Right. So let us now look on some important bond parameters in ethene, which will help us to understand that what is going on with the electronic structure. So there are multiple bond parameters now. First is the bond length. So the CC bond length is 134 picometer, right? And the CH bond length is 108 picometer. So the double bond is 133.9 and the longer one is 108.7. Okay, so I have just round off this and written as 134. Whereas if I talk about the bond angle, then this bond angle is 117 degrees. Okay, so I am talking about this bond angle which is HCH, right? So this bond angle, it is 117 degrees. Whereas the other one is 121.3. So it is written here. Now the question arises, why is this so? Why it is not being the simple case? The reason is that these bonds, if you look at the repulsion, there is a repulsion between the double bond of 2 carbon and the single bond of carbon and hydrogen. Due to this double bond and single bond repulsion, which is greater than the single bond repulsion on the left side, which is CHC, the bond angle has been increased from 120 to 121.3. And due to less repulsion between the single bond and the single bond, that is CH and CH, the bond angle has been reduced to 117.6. This is very important to note down here, that why it is happening, why all of this is happening here. Now this is our bonus topic, which is Bend's rule. So I will try to keep it very simple and very quick because we are lacking time also. The concept says that whenever you take a molecule, the electronegative element always goes to the axial position in the case of trigonal bipyramidal. How? Let us try to understand. Obviously, if your more electronegative is going to the axial, the other will go to the equatorial position. Now, to understand this, let us take the case of PCl3F2. If you look for the steric number, it will be 5, which will give you trigonal bipyramidal. Now, the question is that where would the fluorine go? 2 fluorines are there. Will both of them go to the axial or equatorial, or one of them will go to axial and the other will go to the equatorial? So we have seen the rule right now, and it's the thumb rule that your electronegative element will go to the axial position. Therefore, the correct structure will be this and not this. Now, one more important point. Including your less electronegative substituents, the lone pairs will also go on the equatorial position. I guess this is clear to you. It's very important. This thing is used in predicting the geometries of various molecules where there are more than 2 kind of atoms. So thank you for attending the lecture. I hope you enjoyed the session.